All right, why don't we get started? So, where we last left off, as a refresher, we talked about logistic regression, and in doing so, we needed an expression for pointwise error. And that expression for pointwise error, we're trying to mimic a so-called target probability. And we think of the target function not as a function that outputs a class label +1, -1, but we think of the target function as being a conditional probability of the class label y, given x, the input feature vector. And as such, whenever a +1 label is associated with an in-sample point, that means that more probability is associated with the +1 alternative versus the probability assigned to the -1 alternative. And so we take this sigmoid function, this soft threshold, and we compose a hypothesis as being a weighted combination of feature vectors, but then we pass that score, W transpose X, into that soft threshold, which then maps the score to a number on the closed interval on the real number line between 0 and 1. And so we think of this as a probability, and now our goal with our pointwise error was to try to find a weight vector W, some working hypothesis that best mimics the way the target probability assigns probability mass to the two +1, -1 alternatives that you could have returned by that P of y given x. So we took that expression and we composed a likelihood, and that likelihood used superproduct, and we were trying to find the hypothesis that most closely mimics the probability assignment by the target function across an entire data set. And we made that IID, independent and identically distributed assumption, and therefore we multiplied each one of these pointwise errors together across the entire data set. And so then we took that expression for the data likelihood given a particular working hypothesis using that pointwise error, and we wanted to maximize that likelihood. And this formed the basis of an optimization problem. And we made the observation that if we can pose monotonic transformations, it doesn't change that particular solution point where that expression achieves its maximum. Moreover, we made the observation that if we multiply that expression by a negative number, it changes that maximization problem to a minimization problem. So we did a bunch of manipulation, including logarithm multiplication by a scalar, as well as multiplication by a negative number, and we came up with an expression for in-sample error, which also consequently turned this into a minimization problem. And so this is our expression for in-sample error, En of W, and it's for a particular hypothesis W, an instantiation, a working hypothesis drawn from your hypothesis set. And we had a term for this. We called it the cross-entropy error, right? And it was a measure of the coincidence between the assignment of probability mass to the +1, -1 alternatives associated with each input vector in sample point by the hypothesis, how closely it coincides with the target probability's assignment of probability to the +1, -1 labels. Does that make sense? Any questions about this? So that's where we left off last time. And we took this expression, and this expression has a nice set of properties. It's convex. And because it's convex, certainly we can't take the derivative of this and set it to 0 and solve for it in closed form, but we can use an iterative approach, gradient descent, in order to find the minimum. So in a sequence of rounds, we're going to iterate over a procedure that's going to search through our set of weight vectors, which will ultimately reach some notional best, some weight vector or hypothesis that minimizes this expression. Okay? And so because it is convex, it has a minimum, and moreover, it's not susceptible to the initialization problem that you find with some types of error functions. And so this convexity gives you the ability to basically disregard where you initialize it, which wasn't the case with PLA update for the original perceptron. And so this example represents a convex expression for En, right? And you'll notice here, if you set your solution for some starting weight vector, some hypothesis, and weight vector W for the hypothesis is along the horizontal axis. On the vertical axis, we have our value of in-sample error. And so in this case, and this is an example convex function for En of W, it doesn't matter where we initialize W. We can follow the slope, local slope, and eventually find our way to the minimum regardless of where we initialize. So that's a really nice property. And in fact, if you have an opportunity to design a pointwise error and derive in-sample error from that, as long as you can perform legal mathematical manipulations to get it to a form where it's convex, that's a good thing that you'd want to do with your machine learning algorithms. Okay? All right. So we have this gradient descent, and it has those nice properties. And this is a simplifying case where it has one dimension. But what is typically the case with gradient descent algorithms is you have a much more complex multi-dimensional surface. And so in this particular depiction, we have a two-parameter model, right? So there's the first parameter here along this axis. The second parameter is the other axis on that planar surface. And then the z-axis is the value of, or scoring function, and that would be the value of in-sample error. And so it's very often in real terms that when you have a complex in-sample error or objective function that you're trying to minimize, often you can come into this situation where you have so-called local minima. And so here you imagine this minimization problem is akin to having this multidimensional surface, and you start out with some initial solution that would represent the position of this marble anywhere projected above the plane. And then when you perform gradient descent, you're basically walking down the hill, so to speak. And so you can imagine dropping this marble in some location on the surface, and then it hits the surface and starts to roll down the surface. In the case of gradient descent, you're pursuing that direction down the surface associated with the steepest hill, right? Okay, any questions about this? And so you have a bunch of minima, and the so-called local minima are those minima such that, of course, you're going to reach a minimum, i.e. the gradient gets to the bottom, or the bottom of a pit, if you will. But these are not the minimum of the entire surface. Among these minima, you have certain minima that are local minima, right? But there is one minimum among the minima that is the smallest of them in terms of its value of in-sample error, or the scoring function. Now, certainly the problem is if you're doing gradient descent, you're walking down the gradient, and so you look for this gradient approaching zero, right? Starts to flatten out as your key to when you're approaching a minimum. But depending on your initialization, you don't know if you're near a local minimum or if you're near the global minimum. And so this is often called basins of attraction, right? You have locations nearby a local minima where you start to walk down the gradient, and eventually puts you in that local minima associated with that pit, if you will, right? That cup, that bowl. And the region that starts that ball moving in the direction of that local minima is called the basin of attraction. And essentially what happens in real terms, you're trying to search for basins of attraction such that you'll find a local minimum eventually that is the smallest of the local minima. And so this is easy to talk about and show you, beautiful picture on the board, but in real life, you don't get to see the entire surface. You don't get to see all of En. In real terms, all you can do is evaluate En for your current setting of W. And if you can evaluate En for your current setting of W, you can evaluate En for your current setting of W plus or minus some delta, right? And so what that boils down to, in the case of trying to find this local minima and trying to find the basin of attraction that leads you eventually to a local minima, the best you can do is basically choose a position on this surface and feel around where you are in some local vicinity, right? And so this gradient descent is local, and you don't have access to all these points on the surface. If you did, well, you just pick the one that's lowest, right? But you don't in real terms. All you have access to is the current value of in-sample error, your scoring function, at the current setting, W, current position, and therefore you can go plus or minus some delta around you. Okay. Any questions about this? All right. And so in minimizing our expression for entropy, I almost said cross-country error. It doesn't even make sense. Cross-entropy error. You start at some initial value of W, and that's noted in the book and in the video, and here is W naught. And then you feel around you, and you feel around you by taking a step, some distance, right, which we'll see is eta, in the direction of steepest slope, right, down the steepest hill. So then the weight vector in the next time instant, that's W1, is going to be your initial weight plus some step in the direction V hat of steepest descent, right? So that's that, I had the, analogy of you close your eyes and feel around you. And you could actually, I won't recommend it, if you're out hiking somewhere, it'll take you a long time to go down a mountain, but you could certainly navigate that way by closing your eyes and feeling around. But nonetheless, you're taking a step in the direction of steepest descent, and you're updating your initial weight at each time instant. So there's a recurrence based on that step, eta, in that direction V hat. And so there were some things that we needed to know, and we developed this. Mostly, what is the direction of V hat that we pursue? And so continuing on, any questions about this? So that's to refresh your memory. Continuing on, we started out with an expression, and I filled in that first step because I didn't like the slide from before, and I'll update this on the blackboard. We wanted to compute the gradient of in-sample error. So what is the gradient? Well, the gradient is just rise over run, simple slope, right? It's the change in that function. And so we start out with En at time step 0. We have W naught. And so we evaluate En at W naught. Okay, we get a value. And we subtract that quantity from En at the next time instant, W1, after the update. So substituting for what W1 is, we had the following expression, En of W naught plus eta, our step in the direction V hat, minus En at our initial time, W naught, or at our initial weight vector, or for our initial hypothesis, W naught. And so we then used a Taylor series approximation. And what the Taylor series approximation does, it's a way of simplifying expressions like gradients. And it says, okay, well, if I want to know how much a function has changed, let me assume I have a tangent line at the current location, and I'm just going to walk along that tangent line some fixed distance, right? And so Newton's methods are based on things that arise from the Taylor series. But nonetheless, our step size we know is eta. You're going to take a step eta amount of distance in the direction V hat, and you're going to take it assuming that the local slope is constant, right? Does that make sense? And so also with the Taylor series, we have some higher order terms that we don't really care about. Assuming that your step size is relatively small, you don't have to worry about those second order, third order, and those other terms in the Taylor series. Now I leave it to you if you need a refresher on Taylor series. There's lots and lots of material online. Khan Academy has a module, or it's all over the place, YouTube and so forth. But nonetheless, we can now replace this expression that change in En, we can approximate it using Taylor series by assuming that the slope at En of W at W naught is constant, and we're taking a step in that direction along that constant slope. So this is going to be our replacement, eta times the gradient of En at W naught transpose, and we multiply that inner product with the unit vector V hat that is the direction of the steepest slope. Because if you're going to take a step, if you want to minimize our En, you want to take a step only in that direction that's going to cause you to decrease the most dramatically. Does that make sense? Okay. And so how do we decrease the most dramatically? And this is where we did a little bit of reasoning. Now, if we want to know, okay, how can we take a step? We step in the direction of v hat. Well, of course, that step, eta times the gradient of En at W naught, is in the direction of v hat. And so three cases can happen. It either aligns perfectly with v hat, so it's that vector of the direction of steepest descent, or it's not aligning, or it's completely in the opposite direction. And so one of the questions that we ask, and we asked last time, is what is the smallest way we can take a step in the direction of v hat? And the smallest way we can do that is if this v hat is in the opposite direction of the gradient of En at time at weight vector W naught. And so what does that mean? What we're asking is how big can our step be, right? Another way of saying that is what is the least amount this can be? And the least amount it can be is the largest magnitude negative number, because we're doing this inner product, eta times gradient En of W naught, we're doing the inner product of that with V hat. And so the smallest way we can do that is if this eta times gradient En of W naught is in the opposite direction of V hat. Does that make sense? Okay. So that being said, that means it's going to be at least or greater than equal to negative, because it's in the opposite direction of V hat, eta, which is the step size, times the local slope at W naught, right? Which is the magnitude of the gradient of En evaluated at W naught. Does that make sense? Okay. Any questions about this? Okay, so that's the expression for our step, or how big our gradient of En is going to be. And now we need to know, okay, well, what is this unit vector v hat, right? Well, if this is going to be what our step is, that step has to be in the direction of v hat. And we know its magnitude, okay, well, it's the gradient of En. If we're going to take the gradient of En and we want to know the direction, well, we need to normalize this to make it a unit vector, right? And so what do you do to normalize? You divide that quantity, that vector, by its magnitude, and it's normalized, okay? So here we have v hat is going to be this minus, right, because that negative sign hasn't changed, gradient of En at W naught, because that's the gradient at that W naught point on the surface, over its magnitude. And so here in the denominator, we have the magnitude of the gradient of En evaluated at W naught. Does that make sense? Any questions about this? Okay. So now that we have this unit vector, so now that we have that v hat, okay, we have our direction, okay, so we know what that is, and we have our gradient. And so now, if we think about what happens, this eta here, that eta is going to govern how much you step, how big that step is, how far away you're feeling around to decide the magnitude of your step, right? And so the next question then is, how do you set your step size? Absolutely, cross-entropy error, it's convex. And we said it doesn't matter how you initialize it, you'll eventually reach the minimum. That's true, but there's a caveat. It depends on how you're stepping. Now, there are three choices. You could have eta, the step size, big enough. You could have it too big, or you could have it too small. So let's take a look at this frame on the left-hand side, your left. And on the horizontal axis, we have our weight vector. That's our W. So we're going to have a value along here as our W naught in the beginning, and then W1, W2, W3 as we proceed in our gradient descent over each iteration. So we start out with some initial value W naught, and we have our in-sample error En for that setting at time t0. And so if our eta is too small, what happens? Well, what happens is that weight update, yes, it's in the correct direction. That direction is going to be to the right, but it's going to be so small that each time we make an update in the direction, oh, here I am. It's, I'm so used to doing that, and anyways, I have to remember this, or keep extra batteries in my bag. So yes, we're going to take a step, but you notice here that eta, right, is going to govern how much you step, how much you go to the left or to the right with respect to the horizontal axis. So if eta is too small, what happens? Well, you have W naught here, and maybe it tells you need to step to the right. Well, eta is small, that means you're going to step a very small amount to the right, and then another very small amount to the right, and then another very small amount to the right. Yes, that'll get you to the minimum of this convex objective, but it's going to take you a really large number of iterations to reach it because the step size is too small. Okay, let's take the example. You say, okay, well, I want to jump further away on this error surface because I want to reach the basin of attraction that could be far away from me, right? So let me set eta to be large, some large value. Okay, what happens? Well, you start out with some W naught at time t0. You evaluate in-sample error. You take your gradient, and now you're walking along that tangent line at W naught, tangent line to the to En error surface, and you're making a really large step. So what happens? Well, that tangent line, if you think about it, it's an approximation to what the slope looks like of that error surface. Now, certainly that approximation, if you're going to step out on that constant slope line a really large amount, well, the gradient of that function is going to change. That constant slope is just an approximation. And so if eta is too large, what happens? Well, you'll certainly step a long way away. And we see here in this middle graph, you're going to change your weight vector from time W naught to something at W1 that's really far away. And then something at W2 that's really far away. And something that's W3 that's really far away. And you notice here, you're kind of overshooting what that minimum is and going on the other side. And absolutely, En is getting smaller. You notice here with each update in the center graph, each update to W, En is getting smaller and smaller and smaller and smaller and smaller, right? But you're overshooting. You're jumping too far away. So that's what happens when eta is too large, all right? It could be the case that you get lucky and you just happen to jump far away to something that's right there that you need, and you're done. You're at the minimum. But that doesn't happen very often in practice. Okay. The third thing, what you need, is a hybrid, right? And that hybrid, a good choice for it, is one where eta is variable. It changes over time. And it's really important to have an eta that changes over time for the following reason. I'm going to go back to that beautiful picture of that error surface. So you notice here, you have some landscape, and you don't know arbitrarily where the right place is to initialize it. And we talked about this idea of a set of local minima. You have this local minima, that one, that one, that one, and that one looks like a minimum, but you don't know which one is the global, right? And so if your eta is really large, what does that do for you? It allows for you to jump really far around, far distance in this surface, essentially probing to see if you can find a basin of attraction that could be suitable. Now, when eta is really small, you're not thinking globally in scope. You're only thinking what's nearby to you. So if eta is really small, you just kind of say, oh, let me go locally around here, and I go down my local basin of attraction. And so the idea of starting out with eta being really large allows you essentially to kind of probe over a larger set of regions in your error surface, your in-sample error, your objective function, probing for some basin of attraction. And then once you find a basin of attraction, you make eta small so you can then consider that basin of attraction to try to walk down that hill locally. Does that make sense? Okay, so what we want, therefore, is a step size eta that starts out being really large, ideally, when you're far away from your minimum. And then as you get closer and closer and closer to your minimum, En starts to get smaller. You then make eta smaller, right? And walk down that local basin of attraction. Does that make sense? And so what we really want is an eta step size that scales up or down based on the magnitude of the gradient. If you're far away, the gradient is very large, and you make the magnitude of the step eta really large, so you can jump far to try to find a better one. As the gradient gets smaller, what that means is you're getting closer and closer and closer to the minimum, right, to the bottom of the hill. And that means you're closer to the minimum, so you don't want to jump very wildly, very broadly. You want to jump very small steps. And so what you really want is an eta that adjusts based on the magnitude of the gradient, because by definition, once you get closer to the local minimum, the gradient is going to get closer and closer and closer to zero. Okay? All right. Any questions about this? Does that make sense? Okay. So, all right. So now our step size, instead of taking a step of size eta to change our W, because essentially we take W naught and we add some delta W. And that delta W is some step eta in the direction of V hat, right? And so what does that look like? Well, we know what V hat looks like. V hat, we said, is the gradient of in-sample error at W naught divided by the magnitude of the gradient at W naught, right? That's the direction of steepest descent, V hat. And we're taking a step of size eta in that direction. So we have minus eta, gradient of En of W naught, over magnitude of En at W naught. And that's going to be our change in W. That's what we're going to add to our initial W, okay, in our recurrence relation. So now, instead of that, what do? Well, we said we want to scale it so that it gets bigger when the gradient is bigger, and it gets smaller when the gradient is smaller. So now, imagine then, instead of saying eta, we said A times eta, where that A is going to get bigger or smaller depending on the size of the gradient. So if it gets bigger or smaller, depending on the size of the gradient, what is that quantity multiplying eta? Well, it's going to be the magnitude of the gradient of En at W naught, right? Because that's what it is. You want to scale it. As the magnitude gets bigger, our expression eta should get bigger. If the magnitude of the gradient is smaller, our expression for eta should get smaller. And so what this is doing, and you'll notice there's a color change. I should have said eta and eta prime, right? That would be a little bit better notation. But here, this is the original step, delta W. And what we're doing here is we're saying, okay, let's replace this with a different eta, where that different eta is scaled by the magnitude of the gradient. So in our original eta, you can just call that eta. In our second version, we could say delta W is equal to minus eta prime times minus eta prime times, let's do it this way. So we have now our minus eta, and we have our gradient En at W naught over the magnitude of En at W naught. Okay, this is our original expression. And this does not scale, right, this step size with the magnitude of the gradient. So what we're going to do now is we're going to replace this eta. We're going to replace this eta with a minus eta prime, and that minus eta prime is going to replace this eta. So this eta prime is going to replace that eta, where this eta prime is equal to eta times the magnitude of En evaluated at W naught. Does that make sense? And so, I mean, I'm trying to follow the book. If I had my choice, I would maybe call this gamma or lambda or something else. And I would say lambda is equal to this eta times the magnitude of the gradient of En. I should say gradient of En at W naught. So that way, my new update is now delta W is equal to minus gamma times gradient of En at W naught. And the reason why I have that result is if I'm replacing this with a new learning step, a new step size that can scale, adjust itself with the magnitude of the gradient, so it gets bigger when the gradient is bigger, gets smaller when the gradient is smaller. Well, if I substitute this in here, I'm multiplying by the magnitude of En at W naught. So this numerator and that denominator cancels, and I'm left with the gradient of En at W naught. Does that make sense? Any questions about that? Okay, so I'm trying to match the book here, but a better choice would be to say delta W is equal to minus gamma times this expression, where that gamma is equal to this old eta times magnitude of the gradient of En. Okay? All right. Any questions? That makes sense? Yeah? Okay. So with that, now this new purple version of eta, that's fixed, right? But this original gamma that I'm calling it, or eta prime, you could call it, is going to scale based on the magnitude of the gradient. So in doing so, you're going to have large steps when the gradient magnitude is big, and you're going to have small steps when the gradient magnitude is small, when it's getting closer and closer to that local minima, getting closer to zero. Okay? All right. Any questions about this? All right. So let's take a look at the algorithm. And this is logistic regression. We initialize our weights at the initial time step, and so you just randomly select them. And in a number of rounds or time steps, you compute the gradient. So we had our expression for En of W, and that was cross-entropy error. This is literally just taking ddW of cross-entropy error, right? We see this leading negative 1 over n. We have a sum. We have yn xn in the numerator, and that term in the sum, and we have 1 upon e to the yn w transpose xn. Now, if we look back at our expression, why is this so slow? If we look back at our expression for in-sample error, well, if you take ddW of this expression, well, what do we have? Well, ddW, okay, well, that 1 over n doesn't matter. It's a coefficient that comes out. ddW of a sum, well, the derivative of the sum is the sum of the derivative. And so we take ddW of this log. Well, we do a u substitution. The ddW of this log is 1 over the expression in the parentheses. And then we multiply using chain rule by ddW of this expression. So we have 1 over 1 plus e to the exponent. And then if we take the ddW of the stuff in the parenthesis, well, that's a leading negative number. So that negative comes out here, multiplying 1 upon n. And then ddW of the stuff in this exponent, well, it's just we get a w to the 1 power. And so we have a yn xn that's left in the numerator. Okay? And so that's just a straight derivative of this expression for cross-entropy error, which is just En. Okay. And so we have our gradient of En that we compute by taking the derivative of our cross-entropy error, right? And you can code that easily in something like MATLAB. And then, given that gradient, we update our weights vector. So our weight vector for the next time instant, the next round, is going to be the current version of the weight vector minus eta times this gradient that we just calculated. Okay? And so we keep doing that again and again and again until one of two things happens. Either it's time to stop, some fixed number of iterations, but what is typically the case, you have a halting criteria that says, what was the percentage decrease of En, right? So you look at En from one round to the next, did it change more than 5%? If the change in En was less than 5%, then it stopped, right? Because you're never going to get perfectly zero when you have the change in En. Does that make sense? Any questions? So once you reach your halting criteria, you return your final version of the weights, and those are the weights you use to construct the target, the final best hypothesis, which is a conditional probability, P of y given x. Does that make sense? Okay. Any questions about this? No? All right. So this is logistic regression, and we'll wrap up with this. And this is just a depiction of the relationship between three different versions of a linear model. And we started out with a linear model in the context of the credit approval problem. And we said the linear model was very simple. It is simple. It can't really do much. It can only separate linearly separable problems. And it seemed like it was, why are we doing this? It's very simple. That's really learning. Yes, it is learning. So we started out with classification. And in classification, we had two labels associated with an input vector that described the descriptive factors of customers from historical records for a bank type organization. And our class labels were +1, -1, representing the approval or the denial of credit to somebody. And so we started out with the perceptron, which was just a linear model, W transpose X, and we had a measurement of classification error as being the count of the number of in-sample points for which sign of W transpose X is not equal to the ground truth target function's label for that input in-sample point. And so we looked at our weight update, our learning algorithm, which was PLA, which said W gets W plus YI XI. And we did that update. You can absolutely do that update with a step eta, right? And on an assignment, we saw the impact of what that step does when you're doing that update. But we learned that the hard update can actually damage the progress made by the learner because it can undo a previously correct classification. We did an improvement on PLA by adding that single array, the pocket, and it then exhibited this behavior, what we called anytime algorithm. It got better or stayed the same, but it never got worse. And we saw that when you add a pocket, this very simple change that you can dramatically improve the behavior of the perceptron. Now, we also saw that if you take this linear model that can't separate data +1, -1 points from one another unless it's linearly separable, you can change the geometry. And if you change the geometry through a nonlinear phi function, like a quadratic transformation, you can actually get the benefit of a nonlinear model's behavior out of this simple linear model, but the cost you pay in training is the polynomial time to do the phi function, but the big O of n time it takes to iterate through these in-sample points to train this thing, right? And so here it is, an example that we can take this very simple linear model, right? It's a wonderful building block that you can use to do all sorts of interesting things, okay? And of course, the choice of whether or not you do the phi function or not, we talked about this idea of something being mildly linearly nonlinear or something that's very strongly nonlinear. When do you decide to use a phi function versus just accept the fact that in-sample error is going to be greater than 0, right? Okay, so then we looked at real valued output. And for real valued output, we were looking at regression problems. And for that real valued output, our class labels ground truth were drawn from the set of real numbers. And in doing so, we looked at this as being the amount of credit that they would extend. Certainly, if someone is a bad credit risk, the amount of credit would be 0. If someone is a great credit risk, the amount of credit would be some large real number. Okay, we called it linear regression, and our pointwise error was a squared error loss. It was the magnitude of how different the working hypothesis was from the ground truth real value associated with that input vector. And so this lent itself to closed form solution, and we used a design matrix and some matrix algebra to compute the pseudo inverse, which gave us in closed form solution the final best hypothesis W that satisfied certain conditions, right? And we also then said we can use the pseudo inverse as a good bootstrap starting place for the weight vector in the perceptron. Okay, and so here it is. We changed the pointwise error measure. We changed the label from a +1, -1 binary label to a real value, and now we use the signal directly in a learning model. Okay, so once again, we are taking this simple linear model, and by changing a few things in the anatomy of a learner, we can get dramatically different behavior. Not only can it predict real values, but by choosing the error function, we can make En amenable to direct closed form solution and use that as a nice starting place for the perceptron, which had its initialization problems. Okay, and then finally now, we're looking at this idea of the target function as a target probability P of y given x. And in doing so, the ground truth target function, when we're trying to find a final best hypothesis, we're trying to find a final best hypothesis who best mimics how the target function places probability associated with the conditional probability P of y given x. The probability associated with the +1 label versus the -1 label, how it best mimics the target function that best mimics, rather the final best hypothesis that best mimics how the target function, target probability. Let me say that again. It's just late in the day. In treating the target function as a target probability, we're trying to find the final best hypothesis that best mimics how the ground truth target probability assigns probability mass to the +1, -1 labels for each of the input feature vectors. Does that make sense? And so when we did that, we called it logistic regression. And this logistic regression takes our input signal, our weighted sum, and it puts it in through the sigmoid function, which acts a little bit like a linear regression when the signal is small. It acts more like the hard threshold from the perceptron when the signal is large, whether it's large positive or large negative. But nonetheless, it maps this signal to a value on the real number line between 0 and 1, and therefore we treat it like a probability. And so we use the likelihood as the way of describing the coincidence between a working hypothesis and the target probability. And so we took that and we posed an expression for in-sample error, and then we performed a bunch of manipulations and we treated this max likelihood problem. Ultimately, we got an expression for in-sample error, the so-called cross-entropy error. So here it is again. We treat the target function differently. We add our soft threshold, the sigmoid function, and then we change our pointwise error, and now we have this cross-entropy error, which we can find the minimum for using gradient descent, and this expression for in-sample error was convex, and it lends itself to finding the minimum, and it's not brittle to initializations. And so we did that, and now we're looking at this logistic regression as predicting the probability of default given an input feature vector. Okay, so all of this is to say, here we have the same relatively weak, relatively simple linear model. It makes a wonderful building block, and depending on which aspect of the anatomy of a learner that we tinker with and we change, we can get a dramatically different behavior out of this simple building block. You can change the way you do your pointwise error. You can change the way you're searching. You make something convex, and you can treat it as a probability. You can treat it just as a classification, or you can predict real values. And so here we have the same simple linear model, but just by changing different aspects or different parts of the anatomy of a learner, we can get dramatically different behavior, including this idea of an anytime behavior. Okay? All right, any questions about this? No questions? And so while it's the same model, it's really illustrating the idea that understanding what you can change and how you can change different considerations in the anatomy of a learner, you can get a lot of powerful behavior out of, at the end of the day, what's a very simple model. Okay? All right. So if there are no questions, any questions? No? If no questions, I will end there. And please look out tonight. I'll certainly post on the Blackboard or send out a message from it when I post the assignment that'll be to implement logistic regression. Okay? All right. So I will end there, and we will end early, and I will see you all on Tuesday.